In the previous class, we solved some of the problems on continuous beams. Today we will go for the application of flexibility method of matrix for analyzing the rigid jointed frame. So frame means it is a member which consists of a beam with two columns, right? So to analyze this by means of flexibility matrix, we need to develop the elements of matrix. So normally we are going to follow unit load method to solve such type of problems. So first of all, directly I will take up an example. All of you can open page number 17. Problem number 1. Analyze the rigid jointed frame shown in figure by flexibility matrix method. Vi is constant throughout. So, all of you can take this particular figure. So, end A of the frame is fx1 and the column AB is having a length of 4 meters. Height of the column is 4 meters, that is for the member A. BC is the beam which carries uniformly distributed load of magnitude 40 kilonewton per meter. And the span of this member, it is equal to 6 meters. Then column CD is also on fixed support and the height of the column is taken as 6 meters. So now the first step remains the same, that is determine degree of indeterminacy. So what is the degree of indeterminacy? See, support A is fx1, therefore all the three reactions can exist at support A. One is vertical reaction, horizontal reaction, and a movement. Similarly, D is also on a fixed support. Therefore, there will be three number of reactions: BD, HD, and MD. So, total number of unknown reactions are equal to total number of reaction components are equal to 6. How many equations of equilibrium we have? Equations of equilibrium. That is, we have three number of equations of equilibrium. That is sigma h equal to 0, sigma v equal to 0, and sigma m equal to 0. Right? So, the degree of indeterminacy DOI is nothing but 6 minus 3, that is 3. So now, according to this matrix method, we need to assume, that is, there are 6 number of unknown reactions. Out of them, you can assume any 3 number as redundant forces. Redundant means we are going to determine these redundant forces by means of applying the compatibility equation. That is, we are going to solve the problem for these 3 number of unknown reactions. So, I am going to assume 3 coordinates. I am going to assume 3 coordinates. I will keep maintaining fixity at end A. Then I am going to release the structure. See, I am assuming coordinates. One in vertical direction, this you can call it as VD. Then another horizontal reaction, you can call it as HD, and a movement, that is MD. So, assign the coordinates. For HD, I will assign it as 1. For vertical reaction, I will assign coordinate number 2. And for the movement, I will assign the coordinate number as 3. So this gives you your release structure. See, once you assume these three forces are not there, what the structure is going to become? It is going to become a cantilever frame. It is nothing but a cantilever frame at support A and end B free. So this is the released structure. So I have assigned three number of coordinates, one in horizontal direction, second in the vertical direction, third a movement at D. Right. So now this particular structure, first we will analyze for the movement. See, however, I will be having a table here. I will explain you how to obtain all these elements in the table. So, to solve this particular problem by matrix method, I will have a table. So, in the first column, in the first row, I will say portion, right? Portion. So, I will consider D to C as one of the portion, that is column. Then I will consider the next portion C to D, C to B. So next portion is CB. Then next portion I consider B to A, B to A. B to A. Second row, you call it as flexural rigidity. Flexural rigidity. See, over the entire frame, the flexural rigidity EI is said to be a constant one. So, EI, and for this portion also is EI. Then third one, origin. See, origin means here I am applying unit load in all three coordinate directions and at various sections I am going to determine the bending moment. Similarly, I apply unit load in all these three coordinates and I am going to determine the bending moment. So, origin is D. For the first portion, I am taking origin as equal to D. For the second portion, C, I am considering it as the origin. Then for the third portion, BA, I am considering B as origin. So, this row is also complete. Then next is indicate the limit. See, when I take from here to here, the limits are 0 to 6 meters. Similarly, for the portion CB, 0 to 6 meters. This is the limit. Similarly, for the portion BA, it will be 0 to 4 meters. So, this fourth row is also complete. Next, you have next force M1, M2, M3. Because three coordinates are there, M1 is the bending moment in any portion of the beam due to the load acting, due to the external load, whatever bending moment I get in the portion from D to C, C to B, and then from B to A, I am going to write in this particular row. Similarly, when I apply unit load in coordinate direction 1, I am going to apply only 1 kilonewton horizontal force HD, and then once again I am going to analyze the frame for the bending moment induced. So, these bending moments I am going to write in the column that is M1. Similarly, I apply in the next stage 1 kilonewton vertical force in the direction of coordinate number 2 and I am going to determine the bending moment in various portions of the frame. So those things I am going to enter in the row that is M2. Lastly, I am going to apply 1 kilonewton meter moment in coordinate direction 3, and I am going to write the equation in the form of M3. So this is the table what you need to use. See, now I will come to the first figure. First, due to external load, what is the moment in the beam? See, okay, I will consider separately due to external loads. What is the bending moment induced? This end is free. This end is fixed. This is A, B, C, and this is D. Now, your origin is from D to C, and limit is between 0 to 6 meters. So now, consider a section, say X1, X1. You can show the usual also, right? 40 kilonewton per meter, right? Now I am taking a section X1, X1 from the origin D at a distance, say X from end D. So this particular bending moment equation holds good till this point, that is C. So, will there be any bending moment due to external load when I take the section here? There is no bending moment at all, because you move the section from D to C, you find that no section of the column DC is subjected to any bending moment. Therefore, for the portion DC, the bending moment due to external load is 0. Next, consider origin C and the beam BC. Again, select a section, say X2, X2 at a distance X from the origin. So now, in this portion, uniformly distributed load is acting. So what is the bending moment at this particular portion? It is sagging bending moment. W into X is the load, and this load acts exactly at the center of X, that is X by 2. Therefore, in the portion from C to B, the bending moment, general equation for bending moment is 40 into X into distance, that is X by 2. Or you can write this as 20x square. 20x square. It is positive bending moment. Again, see, now consider section X3. You come to the portion BA. Consider a section anywhere in this portion BA. This section is considered at a distance of X from the origin, that is B. What is the bending moment due to external load? See, external load is acting the entire 40 into 6. So, 240 kilonewton load is acting exactly at the center of the beam. So, what is its effect over any portion here? So, this will have a bending moment in clockwise direction. So, it is nothing but 40 into 6 into 6 by 2. So, you get this bending moment as equal to 720 kilonewton meters. See, now whatever I got in the row M, they use the bending moment due to external load. Next is, I am applying unit load at coordinate number 1. So, I will just rub this. I will go to the next one. I am going to apply the unit load in the direction of coordinate number 1. Coordinate number 1 is nothing but HD, or this we can call it as simply F1. So apply a load of 1 kilonewton in coordinate direction 1. Now you have a section x1 anywhere from D at a distance x from end or origin D. What is the bending moment? See, this will give an anti-clockwise movement about this section. Anywhere, if you take a section, 1 into x with negative side is the bending moment. So, minus 1 into x or simply minus x is the bending moment. Now consider any section. Consider section x2 from at a distance of x from origin, that is C. Right? Anywhere it can be at a distance, say x. What is the moment given by this about any particular section? Again, it will give an anti-clockwise moment of magnitude 1 into distance. Distance is nothing but 6 meters. So, minus 1 into 6 is the bending moment in the portion that is BC. 1 into 6, or you get minus 6 kilonewton meter. Again, consider a section at a distance, say x from end B in the portion B to C. So from origin, let it be x. That I will call this section as x3, x3. So what is the bending moment due to this? See, 1 multiplied by this particular distance I want. So the total distance from here to here is 6. This distance is going to be total 6 minus 6. So bending moment will be equal to 1 into minus 1, because again it gives bending moment like this, minus 1 into 6 minus x, or it is simply minus 6 plus x. Right. So these are the bending moments due to unit load at coordinate number 1. Similarly, now in the next figure, apply unit load in coordinate direction 2. So what is the coordinate direction 2? It is the vertical reaction. So I will just remove this and applying unit load in the direction at D. So apply 1 kilonewton vertical force and repeat the process. Take a section, say x1 from at a distance x from end D. So I am considering from origin D in this portion anywhere. What is the bending moment due to this load? 1 kilonewton. See, 1 multiplied by perpendicular distance between the section. See, this is not the distance. It is coinciding. Therefore, bending moment due to vertical load in this portion is going to become 0. Next, we will have a section at a distance, say, x from end C. Right? So, what is the bending moment? 1 kilonewton force multiplied by perpendicular distance, that is x. So again this gives anti-clockwise moment, therefore minus 1x minus 1 into x. Again you have a section x3 at a distance x from end B or origin B. Now take the moment due to 1 kilonewton force. Force multiplied by perpendicular distance, that is 6 meters. So it will be minus 6. It will be minus 6. 1 into minus 6, you are going to get minus 6 kilonewton meter. Coming to the next step, we will apply 1 kilonewton moment in coordinate direction, that is 3. So apply a moment. Apply a moment. See, I have assumed coordinate in this direction. You can assume like this also. If you assume like this, you will get -1. But according to my assumption, it is a clockwise movement. Therefore, what is the moment due to couple? What is the moment due to couple? So in your elements of civil engineering, you are studying. If a body is subjected to a couple, its effect is same whether you take point here, or anywhere. So this can be proved for a couple. Therefore, the moment at section x1 is equal to +1 plus 1.0. Similarly, as I told you, you take section anywhere, its effect is couple itself, and the magnitude never change. Therefore, it will be +1.0 bending moment. Again, the next portion also it will be +1.0 kilonewton meters. See, my major part of the work is over, right? Now I will give you the unit load method to develop the matrix. See, to develop load matrix and also the deflection matrix, this table I am directly using. So now, displacement due to external load delta M1, delta 1L, displacement due to unit load, external load at coordinate 1, delta 1L is equal to integration between the limits M into M1 divided by EI into dx. So, see, I have all the values for different portions. M into M1 for the portion DC, it is going to be 0 into -x. So it is going to be 0. For the first portion, I will show you 0 because 0 multiplied by -1 gives you 0, 1. Coming to the second portion, plus m into m1, 20x square into -6, 20x square. So integration between the limits 0 to 6, because BC is having a length of 0 to 6, 20x square into -6 dx plus third portion between 0 to 4, m into m1 for the second one. It is 720, m is 720 into m1 -6x minus 6 plus x into dx. See, now integrate between the limits. 0 I will not write it. 20 into 6, 120, 6, okay, 20x square. It should be 20x square, 20x square into 720 into this. Okay, 20x square into -6. Okay, now it is okay. So, now integrate 20, you can bring it outside because it is common constant. Between the limits, integration of x square, x cube divided by 3. Between the limits 0 to 6 plus 720. You can split that into 2, this one. So first one will become 6 into 720. Integration of dx is x plus 720 into x square by 2. I am integrating 720 into x into dx into 720 x square by 2 and indicate the limit. It is between the limits 0 to 4. See, now substitute the limits. 6, x is equal to 6 cube divided by 3 into 20. So, ultimately, on simplification of these two terms, you are going to get delta 1L as minus 20160 divided by EI. Similarly, delta 1L, delta 2L is displacement due to external load at coordinate number 2. This is nothing but equal to sigma m into m2 divided by EI. This is sigma integration of m into m2 divided by EI. So now substitute the things for all the limits. M2 0 0. So I get first term 0 plus integration between the limits 0 to 6 m into m2. M is 20x square. 20x square into m2 minus x into dx plus 0 to 4 m is 720 into m2 is in this case minus 6 into dx. So simplify this particular equation. 20x cube divided by minus is that minus sign I will bring it outside. X cube it will be 20x raised to 4 divided by 4 between the limits 0 to 6 plus 720. Again this becomes minus because minus sign I am bringing out 720 into 6 x between the limits 0 to 4. Substitute the limits of x and simplify. You are going to get delta 2L as equal to minus 23760 divided by EI. Next is delta 3L. So delta 3L is equal to sigma m into m3. Sigma m into m3 divided by EI. So now you can substitute the values of m and m3 for integration. So we will m is for the first portion m is 0. So it will not come 0 plus m into m2 for the second portion 0 to 6. M is 20x square. 20x square. M3 is 1 into dx plus for the next portion BA, the limits are 0 to 4. M is 720 and M3 is again 1 into dx. Right? So now you can go for integration. It will be 20x cube divided by 3 between the limits 0 to 6 plus 720x 720 integration of dx is x between the limits 0 to 4. So you are going to get all the three elements of the displacement equation in the form of delta 1L, delta 2L and delta 3L. So on simplification, okay, EI is missing. Everywhere you bring EI. So I bring 3 EI again by EI, right? So ultimately, you are going to get delta 3L as 357.33 divided by EI. So we got all the three elements of the displacement matrix due to external load. Now, next we will go for development of the flexibility elements. So, coming to small delta 1, delta 2, and so on, we can find these elements by the method what I am going to give next. So, you can say development of flexibility elements. Development of flexibility elements. Flexibility matrix elements. Simply I say elements. So now displacement at coordinate 1 due to unit load at coordinate 1 is equal to sigma m1 square divided by EI into dx for all the three portions. So for the first portion, m1 square for this dc minus x. So integration between the limits 0 to 6 minus x into minus x m1 square divided by EI. Then for the next portion, m1 square is minus 6 square 0 to 6 again into dx minus 6. Okay, m1 square for this portion is minus 6 square into dx plus third portion is m1 square is minus 6 plus x minus 0 to 4 minus 6 plus x into dx. So now you can simplify this particular equation. Minus x into minus x will be plus x square. So x cubed divided by 3EI. X cubed divided by 3EI between the limits 0 to 6 plus second portion minus 6 into minus 6 will be plus 36. Dx integration is x. So I can say 36x between the limits 0 to 6. You can split this into two parts. Minus 6 into dx, it will give you minus 6x between the limits 0 to 4. Again, okay. Here we need to do x square, m1 square, right? So this is not this one. We may need to go for one more step. Okay, I'll expand 0 to 4. 6 2s are, it is 36 plus x square minus 2 into 6x. 2 into 6 is 12x into dx. See, the expanded format, you write it and then go for integration. So here we can keep out EI constant. Otherwise, every time I need to write. So 1 by EI, I take it as common. Substitute the limits 6 cube divided by 3 plus 36 into 6 between the limits 0 to 6. Okay. 36 into 6, no limit, plus integration of 36, you get 36x. X value you substitute for 36 into 4 plus x square. X square integrating you get x cube by 3. X cube by 3 means 4 cube divided by 3 minus 12x square by 2. 12 into x square, 4 square divided by 2. So, if you simplify this complete equation, you are going to get delta 1 as equal to 357.33 divided by EI. Next element, delta 1 2 equals to delta 2 1. Because of symmetry, these things you will get the same. Because it is given by integration, sigma integration between the limits m1, m2, m1 into m2 dx divided by EI. So, for the first portion, m1 into m2, first portion m1 into m2, it becomes 0, right? 0 into something, it will be 0 only. Plus 0 to 6, m1, m2 for the portion BC, CD, minus 1x into 1. So you get minus x into dx. Plus, for the next portion, it will be m1 is minus 6 plus x or x minus 6 between the limits 0 to 4, x minus 6 into m2, that is again minus 6 into dx. So now you can simplify this minus x square by 2, that is 6 square divided by 2, plus multiply this minus 6, again it becomes minus 6x, so minus, I'll use minus sign here, minus x square by 6x square divided by 2 between the limits 0 to 4 plus minus 6 you get plus 36 x divided by 36x, that's all, between the limits 0 to 4. So on simplifying, you get delta 1 2 equal to 204 by EI. 204 divided by EI. Next is delta 23 equals to delta 32, which is equal to integration between the limits m2 into m3 divided by EI into dx. So you can keep 1 by EI outside only, otherwise we need to write every time. So first term, for the first term, m2, m3, see 0 into 1 will be 0. So I will not write that. Minus x into 1, you are going to get minus x only between the limits 0 to 6 plus integration between the limits 0 to 4, third portion minus 6 into 1, you get minus 6 x. Okay, minus 6 into dx. So now integrating this also dx is missing, right? Integration 1 by ei, I keep it outside. 1 by ei into integration of x, that is x square minus x square divided by 2 between the limits 0 to 4 plus integration of 0 to 6, integration of minus 6 into dx, it will be, I will bring minus sign outside, minus 6x between the limits 0 to 4. So now ultimately you are going to get delta 23 equal to delta 32 equal to 204 minus 70 by E. So ultimately you get this as minus 70 divided by EI. See, now we developed almost all except one element of the flexibility matrix, that is delta 33. So once again we need to go for integration. So delta 33 is nothing but equal to sigma integration m3 square into dx into 1 by ei. 1 by ei, we will keep it as it outside. So m3 square, 1 square is 1 itself. So 0 to 6, 1 into dx plus 0 to 6. Again m3 square for second also say 1 into dx plus 0 to 6, 1 into dx. So this will be integration of dx is x only between the limits 0 to 6 plus x only between the limits 0 to 6 plus x only between the limits 0 to 4. This is not 6, so this is 4. Right? So now on simplifying, that is x is equal to 6 plus 6 plus 6. 1 by ei, you can keep it outside. In all the cases, 1 by ei. So it will be 18 by 18 or 16. Okay, it should be 18 by ei. Sorry, it will be, here it is only 4. 6 plus 6, 12 plus 4. It will be 16 divided by ei. Next, I think one more delta 23 equal to delta 32. We got it as. Okay, we need to get this delta 23 and delta 32 as equal to minus 42, not 70, minus 42 by ei. One more element is missing. Delta 13 equals to delta 31. It is equal to integration m1 into m3 dx, sigma m1 m3 dx divided by ei. So now m1 into m1 into m3 for the next one, minus integration between the limits 0 to 6, m1 into m3, minus x into 1, it will be minus 6 into dx plus for the second portion 6 into 1. Again we get minus 6. So 0 to 6 minus 6 into dx plus 0 to 4 minus 6 plus x minus 6 plus x into dx. So as I told you, 1 by ei, you can keep it. Now integrating and substituting the limits, this you are going to get minus 70 divided by ei. See, now all the 9 elements of the flexibility matrix we determined. Next is we'll use computability equation for obtaining the unknown forces, that is reaction, horizontal reaction at D, then vertical reaction at D, and moment at T. So now we can say using compatibility equation, delta into F, small delta into force matrix F is equal to delta minus delta F. See, in this case, it is said to be a rigid frame and there is no final movement, like settling of support. So you can substitute all the elements. You can keep 1 by EA once again outside instead of writing all the time. 1 by EA, delta 11 is 357.33, delta 12 is 204. Similarly, delta 21 is also 204. Minus 70, again 216. Minus 42, and the third row minus 70, minus 42, 60 into F matrix, that is horizontal reaction HD, vertical reaction VD, and the moment T. These are the unknown forces. This is equal to delta due to L, that is 0. This capital delta is 0 for all the 3 forces. So 0 minus 20160. Then 0 minus 23,760. 0 minus 4320. So now you can cancel. This is into 1 by EI. Again here you left. EI is going to get cancelled. So use your calculator to find HD, VD, and FD. You are going to get horizontal reaction as equal to minus 23.69 kilonewton, and vertical reaction VD equals to 121.98 kilonewton, and MD, moment at D, is equal to minus 53.44. What this minus sign indicates in the answer, we have assumed certain direction. Say for example, horizontal reaction, we assumed it to be towards right, but we got negative, therefore it should act towards left. VD, okay, upward reaction we assumed, we got the positive answer. MD, we assumed clockwise, but it is anti-clockwise, minus sign. So now, knowing these three, you can calculate the remaining forces. See, horizontal reaction is acting like this. It is 23 point. I change the direction, so I write it plus 23.69. Vertical reaction All of you can see it. Okay. Okay, vertical reaction 121.98 and moment I got reverse. I think we assumed clockwise, so it is 53.44. The reaction HA, then VA and MA. I will assume some that for MA. Okay. And UBL is of 40 kilonewton per meter. See, use three conditions of equilibrium. Sigma H equal to 0. Only two orbital forces are there. Therefore, HA equals to 23.69 kilonewton. And equate sigma V to 0. So if you equate sigma V to 0, VA plus 121.98 is equal to downward load 40 into 6. So you are going to get the vertical reaction at A as 118.02. 118.02. Use the third condition of equilibrium, that is sigma m is equal to 0. So, taking moment about A, equate sigma MA to 0 in this figure. So, MA, I have taken it as clockwise. Okay, I will treat it as clockwise as positive MA minus 53.43, that is this moment. Then moment due to this HB. Again, it is like this. Therefore, minus 121.98 into 6 meter. This goes into distance. Similarly, HA, it gives clockwise movement. Therefore, plus 53.44 into distance. See, this is the distance, 2 meters into 2. Again, UDL gives clockwise movement. 40 into 6 is the load. Where it acts exactly at the center. From here, what is the distance? Perpendicular distance is this into 3. See, this must be equal to 0. So, from this particular condition, you can determine MA. If your assumed direction is correct, then your answer will be positive. If your assumed direction is wrong, you will get negative. So, change the direction.